So welcome everyone. We will have today as our speaker, distinguished speaker, Dr. Laurence Rilett. He is also one of my dearest friends. So I know him for a long time, and his work has always amazed me. So for his short bio, Dr. Laurence Rilett, distinguished professor of civil engineering and holder of Keith Klausmeyer Chair in Engineering and Technology at the University of Nebraska-Lincoln, is the director of both the UNL Mid-America Transportation Center and the Nebraska Transportation Center. Dr. Rilett's research is in the field of intelligent transportation systems, applications, as well as large-scale modeling. Dr. Rilett has been a principal investigator or a co-principal investigator on more than 40 research projects and has authored over 90 referee journal papers. He is currently the managing editor of the ASC Journal of Transportation Engineering Part A and the vice president of the Council of University Transportation Centers for 2020-21. And one note, I have always used Dr. Rilett's work in my research. So he's a very distinguished scholar in our area. So we are very glad to have him to speak to us today. Thank you. Dr. Rilett. Yeah.
Great, thanks, Ronnie. I appreciate the introduction. And as indicated, let me start sharing my screen. Give 1 second. I'm going to be talking today about estimating and forecasting transportation metrics. The title has lessons learned in there, so I'm going to give it a fairly level. But if anyone has any questions on the details of what I'm going to talk about, I'll be happy afterwards to go over them. So by way of overview, I'm going to talk about two primary areas. The first is the Highway Capacity Manual, the 6th edition, and its use of traffic microsimulation and other types of simulation models inside. So particularly looking at passenger car equivalents and capacity adjustment factors. I'm also going to look at arterial street travel time reliability metrics. And then I'm going to finish with some talking about some of the effects of COVID-19. Not so much the changes, but how the travel time metrics are affected by them. The focus is on lessons learned from the U.S. Midwest. As Ronnie indicated, I'm from Nebraska, but I believe that the lessons I'm going to talk about actually apply across the country. And then I'll finish with some concluding remarks about some of the future research topics. So the first thing I want to talk about is the freeway capacity and passenger car equivalents from the HCM6. The PCEs, as you all know, are used to translate observed mixed vehicle flow rates to passenger car only flow rates. We use them extensively in engineering practice. The HCM6 is based on equal capacity method, and I'll describe that in a few slides. And interestingly enough, it's the first HCM that's based entirely on microsimulation results, in this case from VISSIM 4.4. This is the setup for the modeling that was done in the HCM6. You can see that this is the standard model they use. They have an 8-mile section of flat. Then they have grades, and they have detectors at different lengths so they can model what goes on at different grade lengths. And then they have a level section at the end. And they basically did a lot of simulations. I'll talk about how many in the next few slides. But this is the general setup. They can change the grade. They can change the grade length. They can change the volume, and the output from these simulations are what went into the HCM6. So when you're using PC values from HCM6, it's actually from a VISSIM model, and we'll go in more detail in a few slides, but I wanted to point out that this is a rather new way of approaching capacity and PCE calculations. It's a lot of innovation involved with it. What's interesting from the Midwest point of view is that the HCM6 was set up for 3 lanes in each direction, and that the desired speed was 70 miles for all vehicle types, cars and trucks. And I'll explain to you why in the Midwest this may have some issues when we go to use the values in the HCM6. Here are the key parameters for the VISSIM model. I only put this up not to go over each one of them, but to show you how detailed it is. Geometric data, there's vehicle parameters, there's traffic flow parameters. It's a fairly sophisticated approach, as anyone who's used VISSIM would know. There's also driver behavior, data collection parameters, and simulation procedures involved. I'm not going to go into any great detail. I did highlight one, though. The aggregation interval was 1 minute. So when the developers of HCM6 were developing the passenger car equivalents and the capacity values, they went with an aggregation level of 1 minute, which is new for the HCM6. Historically, it's always been at a 15-minute level. And that was noticeable to us. And I just wanted to point it out because some of the numbers may not coincide with the ones we're used to because they chose a different aggregation level. So to do the analysis, to get the PCE values, they ran a number of scenarios using the VISSIM 4.4 model. They did a number of passenger car only conditions, 91, so 13 grade levels and 7 distance levels. They looked at 3,549 scenarios for mixed traffic, so cars and trucks, so grade levels, distance levels, truck percentage levels, and truck composition levels, the trade-off between single unit trucks and tractor trailers. So all told, they did 3,640 scenarios or 3,640 runs using that VISSIM model I showed earlier, that geometric design they were using. Once they got that, they could go through and calculate the PCE. And what you're going to see, is that the PCE value is a function of the capacity values obtained from VISSIM. So for those 3,640 runs, they developed the capacity from that, and from that, they calculated the PCE. It's easiest, so I think, if we show it by example. So in this case, I've taken a truck percentage of 20%, a truck composition of 30% single unit, 70% tractor trailer, a grade of 3%, and a grade distance of 1 mile. Okay. Once you have those parameters set, you can go and run your simulations, which is what the developers did. Here's the passenger car only results. These are simulation results. On the y-axis is flow rate in vehicles per hour per lane. On the x-axis is density in vehicles miles per lane. They ran different volumes. The green ones are low volumes. The red ones tend to be higher volumes. But you can see it's a fairly standard linear flow rate density curve. From that, they calculated capacity, and that's the red line at 2,268 vehicles per hour per lane. The other key point on this figure that you'll notice is that in HCM6, they took capacity when calculating PCEs as the 95th percentile flow rate instead of the 100th percentile. And it's our understanding this is the first time this has ever been done in the HCM. I could be wrong, but it was unique to this characteristic, or to this section of the HCM. So basically, they do the run, they get the capacity, they can then run it for mixed traffic. In this case, again, it's 20% trucks, 30-70 ratio, flow rate on the y-axis, density on the x-axis, capacity is the 95th, a fairly standard flow rate density curve. And again, they went through and calculated the capacity for this scenario is 1,764 vehicles per hour per lane. Okay. Once you have those two capacities, so you do your conditions, you get the capacity values, they then calculated a capacity adjustment factor, or CAF. And basically it's just the ratio of the mixed flow to the passenger only flow for the same conditions, same grade, same length. And you can see for this example I gave, it's 0.78. So the capacity is basically 80% of the passenger car only for this scenario. Once you have these CAFs, you can then go through and calculate the PCE for this passenger car equivalent for this scenario. Again, it's equal capacity method. There's a formula for it. I'm not going to go into great detail on it. It's in the literature. But essentially for this example, the passenger car equivalent is 2.43. So essentially what it's saying is for a typical tractor trailer under these conditions, one tractor trailer is equal to 2.43 passenger cars. And of course, they're going to do this for all those combinations that I talked about before. It's a little more complicated, and I'm going to show that on the next slide. So when they calculate EC PCE values in HCM6, they do this. This is what I just described. They go through and they do the simulation runs and get the capacity. Calculate the CAF, which I showed. There's actually a step 3 where they take all those simulated CAFs and they develop a multiple linear regression model, and they use that to estimate CAFs, and then from that calculate the passenger car equivalent. So they don't use the simulated CAFs. They do an extra step where they run a multiple linear regression, calculate the CAF, and then calculate the PCE. And these are the values, the output from this are the values you see in the highway capacity manual. So that's by way of introduction. What I want to do now is just talk about some of the work we've done with this, with the HCM6 approach. The first analysis we did was for the Midwest. Okay, so basically the HCM6 was developed for East Coast assumptions. There are 3 lanes of traffic in the interstate on each direction. And the question we had is, well, what about the rural Midwest? Are these values appropriate for where we're at? And I'm showing Nebraska because that's where we collected the data. But essentially, I'm arguing that anywhere where you have 2 lanes in each direction and low volumes, so outside of cities, has the same types of considerations. So we went out and collected some data. We have a number of ways of collecting data at University of Nebraska. We have a van, we have trailers, we have automatic data collection. One of the things we collected out in the rural areas was the free flow speed distribution. So we went out and estimated free flow speed. This is a cumulative density function. So the cumulative percentage is on the y-axis from 0 to 100. The speed is on the x-axis in miles per hour. And you can see this is the distribution for passenger cars. The mean is 72%. The 85th percentile, sorry, 72 miles per hour. The 85th percentile is 77 miles per hour. So fairly high, but remember in the rural parts of the U.S., the speed limit's 75 miles per hour. So these free flow speeds are not unusual. They're fairly specific. And remember that the HCM6, they assumed that all vehicles were going 70 miles per hour. That was their max speed. We collected it all as well for single unit trucks, and you can see that they're going considerably slower, an average speed of about 66 miles per hour. And then we calculated it, or we estimated it for tractor trailers, and the tractor trailer average speed was 64 miles per hour. So you can see there's a movement of the cumulative distribution to the left, meaning all the vehicles are going slower on average. And the natural question is, if the vehicles are going at a different free flow speed, does that have an impact? Remember, HCM6 assumed they were all going the same speed, and what we're seeing in the field is they're different. These virtual presentations are always tough because you can't really ask questions, but assume that I'm asking you a question like, why would the trucks be so much different than the cars? And the answer is because in the United States that most of the trucking firms, almost without exception, have speed regulators or governors on their trucks. So even if a driver wanted to go faster, they couldn't. Okay. And the governor is usually set around 65, 66, 67 miles per hour. So they couldn't go, that's the maximum speed they're going to go. So you have this sort of discontinuity where you have these cars wanting to go very fast and the trucks going much, significantly slower. So the next question is, does this matter? And on the left, you can see a video that we took on some of our data collection. On the right is a simulation showing essentially the same types of things. And what you find in the Midwest, if you've driven anywhere on these 2-lane interstates, 4-lane interstates, 2 in each direction, is that these trucks will pass each other, and one will be going 65 miles per hour and one will be going 64. It'll take forever for them to pass because it's their speed differential. And what happens is you get these moving bottlenecks. So you get cars behind the trucks as they pass, and they can't go the speed they want. So the question we have is this captured in the HCM6? The other thing to note on this slide is that out in the Midwest, throughout the western part of the country, we get a lot more trucks, percentage trucks, than on the East Coast and West Coast. So it's not uncommon for us to see 50% tractor trailers on our interstates in the western part, and even in a fairly populous area, we get 20 to 30%. Mainly because we're a major transportation corridor. A lot of commercial vehicles are using the roads. So what we wanted to do was say, well, HCM6 is great. We have this simulation model. Let's take the HCM6, their approach, replicate it entirely, but for Midwest conditions. So instead of 3 lanes, we're going to do 2 lanes. Instead of the truck lengths being set, we're going to use the ones that we observe in the field. Instead of the desired speed being 70 miles per hour, we're going to use the empirical speed distributions that we saw in the field. The other thing I wanted to point out is that the HCM6 was developed with the VISSIM 4.4, which is no longer available. At the time we were doing this work, we had VISSIM 9.0. And so we had to spend a bit of time making sure that the results we got from VISSIM 9.0 also were compatible with the original HCM6. And I was happy to report that for our consideration, 9.0 was able to replicate 4.4. And this point will come important in a few more slides. But for now, the 9.0 was able to replicate the highway capacity manual results using 4.4. This is a slide of the results. So we went through and did the exact same thing the HCM6 did, but only with Nebraska conditions. This is the graph showing the passenger car equivalent on the y-axis versus truck percentage on the x-axis. The HCM6 is the green values down here. And if anyone's looked at the HCM6, generally it's about 2.25 to 2 passenger car equivalents. That's the number that you would typically see in the HCM. And remember, the HCM only goes up to 25% trucks, which is, in the western parts of the country, we often get a lot more. And the thing to notice about it is the red curves are what we were experiencing in Nebraska. And on average, it's about 54% higher. And the reason for that is, just as you would expect, we have these moving bottlenecks, we have differential speeds, and they are affecting the ability or the capacity of the system, how many vehicles you can get through. And we were picking that up in the simulation models, and anecdotally, we were seeing that in the field as well. The great thing about the HCM6 approach is that you can do lots of different sensitivity analysis. If you have different speed limits, we can rerun everything with the different speed limits. And as you'd expect, as speed limit goes up, so if you're in Texas and you have 80 miles per hour, the passenger car equivalents are actually higher. And the speed limit goes down, you have 70 miles per hour in your area, the PCE values go back down closer to what's in the HCM6. Although you can note that they're not exactly the same. You can also do analyses on truck lane restrictions. Can you go through and say what happens if we restrict passing? This came about when I was talking to one of my European colleagues, and I was explaining what we were doing, and he was saying, well, I don't understand the problem. And I explained again, we have these trucks passing each other, moving bottlenecks. And then after a while, it turned out that in Europe, they don't allow trucks to pass for this very reason. The trucks go slower, they're not allowed to pass, so they have to stay in the right lane. If you do that, what this graph shows is that the more restrictions you put on, the smaller the PCE value. And if you completely restrict passing, you actually get very close to the HCM6 values. So the lesson there is if you restrict passing, you don't allow these trucks to pass each other, then the HCM6 values would work very well in Nebraska. But since we do allow trucks to pass, they're off by about 50%. The second one I wanted to talk about was the step 3 of the model. So the freeway capacity, I'm going to talk about the same thing on HCM6, but step 3. And if you remember step 3, step 1 and 2 is running the simulation model. Step 3 is the multiple linear regression model, where they relate the CAF, the capacity adjustment factors, to a number of variables. If you read the original documentation for the HCM6, they actually have 15 parameters. This is the model. I'm not going to go into all the parameters and the details behind it, but you can see it's fairly extensive. It also explains why we still have tables in the HCM6. One of the things is you have this great model. Maybe you could have put the model in the HCM6, but it's just too complicated to use. So they opted for the tables. What we were curious is could we come up on this step 3 and come up with a simpler model? So we did go through. We've come up with a proposed model that only has 6 parameters. On this graph here shows HCM values, HCM6, and our proposed model, and you can see it's a fairly straight line. This is all the values from the table in the HCM. The average error was about 0.5%. One of the things we're advocating for in the next HCM is to get rid of the tables, come up with a simpler formula that works, and then you can just plug in your values to get your PCE. So you can plug in the numbers you want rather than trying to interpolate and extrapolate from tables. So that's one of the things that we did. So the lesson is you actually can make these modeling a bit simpler. And again, it comes about all because they're doing simulation. Trying to do this with actual empirical data is a bit of a problem. The last thing that's really interesting about the HCM is that you can do new things. You can do, in this case, connected and automated vehicles. We were looking at platooning, so the effect of truck platooning, obviously very important in Nebraska. What's great is a lot of people go and do CAT, we're going to do a connected vehicle analysis, and then they'll compare it to the HCM, but we're never quite sure is it the difference is because of their model or because of the connected vehicles. So what we wanted to do is use the exact same methodology, calculate the PCEs, same truck characteristics, everything else, and see what happens. And the findings, well, as you expect, the PCEs for connected vehicles are about 34% lower than the HCM6. The key finding of that is you can actually compare it using the same approach used in the HCM. You can put in the vehicles, the trucks operating differently, and then make a apples and apples comparison. There was also the issue that we found, and this is a lesson learned, is that VISSIM, to do the platooning, the connected vehicles, you need VISSIM 20. It's not backwards, it's not compatible with VISSIM 9 or VISSIM 4.4. So if you took VISSIM 20 and tried to replicate the HCM6 analysis and get the PCE values, you will not be able to do that because they made changes. We were able to find some workarounds so that we could use 20 and do the comparison, but it took a bit of work. And the lesson there is when you're using simulation to do something like a national standard, you really have to make sure that you have access to that simulation model for later work. Otherwise, you may get yourself into trouble. And the other finding was that the regression formulas that were used in the HCM might not work for CAVs. And so we came up with our own equations, our own regression models. I now want to talk about the HCM6 reliability on urban corridors. The motivation is looking at travel time on arterial roads. And really what we want to do is compare the HCM6 methodology with empirical data. There's a lot of definitions on travel time reliability. Here's one from FHWA. It measures the extent of unexpected delay to drivers. So it's the consistency or dependability in travel times is measured from day to day or across different times of the day. For traffic engineers, what this means is that they're going to be looking at the travel time distribution and trying to come up with a way of using that to describe reliability. So rather than just looking at the average travel time, they want to look not only at the average, but the distribution or the variance. This is in chapter 17. It's a very important step forward for arterial travel time analyses. What it allows you to do as an engineer is to go in and estimate the mean of travel time, estimate and forecast the mean, the variability, and reliability performance measures. What was interesting is in the literature we could find no papers or reports where they compared the approach that they put in the HCM6 to any empirical data. So we were curious on whether it would work in our area. With this approach that they developed, would it be okay to use in Nebraska? Here's the approach, and this is a graph basically taken from the HCM6. You put in a number of inputs: demand, capacity, traffic count, free flow. So you go to your corridor, you collect a bunch of input data. you have a number of scenarios looking at different demand patterns. You're looking at different weather events, different incident occurrences. And you do a Monte Carlo simulation. You do a bunch of different weather. Here's the weather on this day. Here's the work zone on this day, on this date time period. And you just run it over and over for, let's say it's a 6 month, over the entire 6 months, could be a year, over the entire year. Okay. And each of those scenarios, you use the HCM evaluation method to get the travel time. So once you've done all these Monte Carlo simulations, you can actually come up with an average travel time distribution. Okay. And from that travel time distribution, you can then go and get travel time reliability metrics, buffer index, planning time index, travel time index. I'm going to go into more detail about these in a few slides, but essentially they're trying to measure how reliable is this corridor given this distribution of travel times. To show you an example, this is a cumulative density function for eastbound Dodge Street in Omaha from 2019. The red line here is what we estimated from the HCM6. So here's the travel time distribution using the HCM6 approach. We then went and got some empirical data. In this case, it's INRIX data. We've also used Bluetooth data. The findings we had are pretty consistent across the platforms, whatever empirical data we're having. So you can see the INRIX data here. And when you look at the graph, you can plainly see that they're not very close to each other. And what's worse is that the HCM model is saying that the corridor is very reliable, right? Very little variability. But when we look at the actual data, there's a lot of variability. We repeated this. We thought at first when we did our first one, oh, we just picked the bad corridor, right? So we picked 5 test corridors in Omaha and Lincoln. We looked at 9 scenarios, eastbound and westbound. And what we found is that we underestimated the mean on average by 10.6% using the HCM procedure with a range of 1 to 31%. The variance we underestimated by 51% with a range of 14 to 83%. And the reliability of the travel time metrics that I provided were underestimated by 10 to 50%. And in general, the more congested the corridor or the arterial road, the worse the results. Okay, so these were not very beneficial. That what we found is that the HCM6 reliability method really didn't apply to our cities in Nebraska. So then we thought, well, is there a way to calibrate the model? Can we go through this fairly complicated program and just get our results, change the model parameters in the HCM6, come back, run it? So just run it over and over by changing the parameters and get a calibrated model. And the answer is yes. This shows the same corridor, eastbound Dodge Street. And you can see the red is what the original HCM was. The blue line, the solid blue line, is the calibrated HCM compared to the INRIX data, and they're almost spot on. And similar results in all corridors that we examined, all those scenarios that we looked at, we could calibrate the HCM model. So on one lesson, for us, the HCM6 reliability model didn't really work very well on our arterial roads. But if we were able to get arterial data, we could calibrate it so that we could replicate what we were seeing in the field. So the lessons learned, HCM6 is very innovative. It uses simulation, VISSIM, and Monte Carlo. Very powerful. We can now go through, instead of having one set of PCE values, we can actually calculate PCF values for different parts of the country for their local conditions. So that's the strength of it. The negative of it is you have to go through, in our opinion, it shows the importance of going through and validating and calibrating the results rather than just taking them and using them. There's also the issue of compatibility. If we're going to use VISSIM, for example, in the HCM, in this HCM and in future ones, I think we really have to understand that as VISSIM changes, we have to keep up with those changes and make sure that we always have the version we use to calculate values in case someone wants to go back and replicate or change them again. And as I said, VISSIM 20 gave us different results than VISSIM 4 and 4.4 and 9 when we were using it to estimate HCM values. What's great about it is you can do new studies, and we showed it. We showed the CAV analysis earlier. We showed you the 4-lane freeway. And if there's something unique in your area, you can go through, take the HCM and come up with values that fit your specific application. The next steps, we're looking at transferability. Can we come up with a calibration that works both temporally and spatially? So we know we can calibrate, but can we do one that we can use to forecast? And we're also looking at new approaches for travel time reliability. So that was HCM 6 part of the discussion. I also wanted to touch briefly on some of the work we're doing with COVID-19 pandemic and travel time reliability metrics. The pandemic, as awful as it's been, is actually, you know, if you're looking for some benefit to it, which there aren't any really, is that it is a natural experiment for researchers. You know, people have looked at is travel on U.S. roadways safer during the pandemic. So what's happened is crashes have gone down, and you could argue that because crashes are gone down, that it's safer. But volumes have also gone down, and the volumes have gone down a lot faster than crashes, with the result that the crash rate during the pandemic has actually gone up. And so the natural question is, it's safer? Well, crashes are down, but the crash rate is up. What I'm going to talk about today is looking at what the effect of the pandemic had on reliable arterial roadway travel times. So, you know, volumes are down. In Nebraska, they were down on the order of 20 to 30% across the state. Did the pandemic result in more reliable arterial roadway travel times? And if so, what the question we had is, which travel time reliability metrics are the best to use, right? So we, similar to before, we got INREX travel time data from a number of roadway corridors in Nebraska. We looked at the peaks, AM and PM peak. We looked at 15-minute subperiods. We looked at average travel times. And we looked at March, April, and May from 2018, 2009, not the pandemic, and then 2020 during the height of the pandemic. We looked at 4 corridors, 2 peak periods, 2 directions, or 16 scenarios. I'm not going to go over all of them. I'm going to talk about this one, testbed, Omaha Dodge Street. It's actually part of the National Highway System. And US 6 has a fairly high AADT of about 80,000 vehicles with a PM peak level service of F, so fairly congested. And so I'll show this example. I'm not going to show all 16 scenarios, but I'll show one. Here's westbound Dodge Street AM peak. On the y-axis is average 15-minute travel time for the test bed. On the x-axis is 3 years, 2018, 2019, and 2020. It's a standard box plot where the black line is the median. The box shows the 25th and 75th percentile. The dots show outliers. And just looking at this graph, you can see that there's a noticeable difference in 2020. Not only is the mean, lower, the median lower, but the distribution is smaller. And you can see it in the numbers. The mean dropped by about 16.7%, and the standard deviation of travel times went down by about 50%. So a lot less variability during the pandemic than non-pandemic. And of course, most people go, yeah, of course, that's sort of what everyone's experience was. There's not a lot of traffic. It's easier to get around. We looked at all 16 scenarios. The average drop in mean was from 7.1 to 23.2 with an average 14% drop. Standard deviation, 16.5 to 69.4% drop with an average drop in standard deviation of about 43. As I said earlier, there's lots of definitions of reliability, but our conclusion was that the travel times became more reliable no matter what definition you wanted to use. The mean's down, there's less variability. Almost any citizen would say that the roads are more reliable. So given that intro, the next question we wanted to look at was, what about the metrics we use to measure reliability? So we sort of showed that reliability is better. What about the metrics we use? It turns out U.S. transportation agencies, by and large, don't use common statistical metrics. They don't use mean and standard deviation, as I just described. The general argument is that users won't understand it if we use statistical terms. So they've come up with a wide range of metrics. And There's travel time index, planning time index, level of travel time reliability, buffer index, and there's more, but these are probably the four most popular. Travel time index is the mean travel time over the free flow travel time. The planning time index is the 95th percentile travel time over the free flow travel time. So, you know, one is how's it on average does it compare? One is how, you know, what's the worst you can do compared to the average when there's no one around? The level of travel time reliability is the ratio of the 80th percentile travel time to the 50th percentile travel time. So some measure of variance to some measure of mean or central tendency. The buffer index is the 95th percentile minus the mean. So this variability, like the variance is a measure of variance is 95th to 50 to the mean is a measure of variance over a measure of central tendency. So how much spread is there versus the average value? So the question I asked at the beginning was, were the arterial roadways more reliable during the pandemic? So we looked at the average across all those 16 scenarios. So for all the arterial roadways we looked at, and we found that the TTI dropped 14%, the planning time index went down 19%, the level of travel time reliability went down 3%, the buffer index went down 34.3%. So the answer to were they more reliable really comes down to what metric you use. And it shouldn't be surprising that they're so different because they all measure different things. And it comes back to that we don't have a common definition for reliability. The other lesson I wanted to point out is the one that showed the least difference, the level of travel time reliability of only 3%, is the one that FHW uses to measure reliability in the field. It's actually put into MAP 21 into the FAST Act. Okay, and so our argument is, is that most people would say reliability improved during the pandemic, and we are using metrics, travel time reliability metrics that actually don't pick up that change. So I think it's a good opportunity for us to look and revisit these decisions on what reliability or any metric measures, right? If it can't pick up these changes, it's really going to pick up future changes. And we have our own, I'm not going to go into it here. My own belief is that we should really stick with statistical measures when we're measuring reliability rather than using these types of metrics. But again, that's a philosophical argument, not an engineering argument. So lessons learned, COVID-19, and we obviously had a profound effect. It's a natural experiment. Crash rates up, are we left safe? Travel time reliability is about the same if we use the level of travel time reliability metric. Is that really accurate? So the lesson from my perspective is that reducing complex systems to simple metrics can be misleading. And what I always tell my students, know your data and know your statistics in order to make meaningful inferences. So it's great to go use these numbers and say things, but I always try and look at the actual data and make sure that the data and the metrics are actually going with what my feeling of what's going on the system. So in terms of the concluding remarks over the entire talk, as I said before, I wasn't going into any great detail on any of the models that we were developing, but I'd love to follow up with anyone if they did. I was looking at it at a much higher level in terms of the lessons that we found. Simulation is great. It can be applied anywhere at a very low cost. The HCM has begun to adopt these. It's very powerful, and I hope I showed that. We can actually do HCM6 work on our own local areas, but there are challenges, and the challenges are really calibrating and validating it to local empirical data. But I think this is a real opportunity for us to develop regional values from the HCM6, and it may be in the future, instead of having a set of tables, we just have a set of tools we can use to get the values for our specific application. The lesson calibration, skipping calibration is always a bad idea. Calibrating the local conditions, I think, is a good idea. It's certainly good in Nebraska, and I would argue it's good across the United States. And really doing the calibration of the specific applications is really critically important, in my opinion. I'm going to leave it with a general piece of advice I always give our students. It's actually a famous statistician, Box, who said it, all models are wrong, but some are useful. I think it's easy to show that some of the models we have give incorrect results. But I think by calibrating and validating, we can certainly make them more useful for the regional areas. So are the simulation models useful for the given application? I hope I showed that it can be, but only if we take care in calibrating and validating them to the application we're using. I've talked a lot about we when I was giving this talk. Antonio Hurtado Beltran is about to get his PhD. He's going to be a professor, go back to his home school in Mexico. He's a Fulbright scholar at UNL. He did a lot of the work in here, as well as Dr. Ernest Tufor, who's a postdoctoral fellow at NTC. Dr. Li Jiao, who's also a postdoctoral researcher, who also did a lot of work on here. And then Sean Murphy is works at HDR. He's a graduate research assistant finishing up his master's. And a lot of the work I showed today was based on their thesis and their dissertations. I also want to thank the City of Lincoln and Nebraska DOT for the data and the paper reviewers that we used who gave us great comments back. And a special shout out to the HCM researchers. They were very generous in sharing the developers, the ones who developed these approaches. They're very generous in showing how they did their work and sharing their results. I think it's a real plus that we're developing this new way of approaching the HCM6, where we can actually go through and do local calibrations and get numbers that fit our applications instead of trying to have one model for the entire US. With that, I'm going to end my talk. I really appreciate you listening today. I know these virtual talks can be tough, but I'd be happy to answer any questions that you have.
Thank you, Dr. Rilett, for this awesome presentation. I learned a lot, and I hope the audience also learned a lot. So right now we are opening up our question answer section, and you're welcome to type your question in the chat box, or you can unmute yourself and ask that directly. So one question that I have in the chat box is from Pingjiao Zhao. She's asking that, it's not a question, but she just wanted to share that from SCDOT, what she heard that in 2020, although crashes went down, total fatal crashes actually went up. So
okay.
his is that, so was it really safer on road during COVID? Maybe not.
Yeah, I think that's a good point. And I think most people would argue that it wasn't safer. Ironically enough, what we found in Nebraska was the number of speeders was way up, the number of distracted and impaired drivers was way up, and that was causing the increase in fatalities. So yeah, I would argue it isn't, but sometimes you look at it and the numbers aren't quite clear. But thank you.
Yes, thank you for that. Any other question? I personally have a question. So, Dr. Rilett, you showed that in the HCM6 we have the ability to do the connected vehicle modeling. So, connected vehicle, there are different factors that affect the performances, like the communication, the real world environment affecting the communication. So could you please elaborate a little more how all those were included in that HCM6 modeling?
Sure. Let me find it. Sorry about that. Let me just come to it. So I only took it a few slides. This is actually Antonio's work looking at these, and we're examining different aspects of it. What I really wanted to get across is that it is possible to take the HCM6 methodology that was used to develop the PCE values in the HCM and use the exact one, everything exactly the same assumptions. They give the same results for passenger cars and put in different variations of the CAV technology. In this case, we were using this platooning from the coexist. If you didn't like that, you could put in any one that you wanted. How do they communicate? how close the platoons get together. Is it always have to be the same trucks? Can they be different trucks? All of these are sensitivity analysis you can run. And so in our case, when it was 34%, we had a series of assumptions that we liked. But I guess the point I really wanted to make was if you didn't like our assumptions, you had your own model. It's very easy now to go in and do this, run the model, and then compare it to the HCM6 values. Right now, the issue, in my opinion, is that people will run simulation models compared to the HCM6, and you're comparing apples and oranges because they're not all the same assumptions. So it's a good question. What I like about the model is that we can go through and do anything we want, and then we can argue, well, what about communication? How close to the platoons created? Are there any rules on maximum size? All of those things are looked at. I just didn't cover them in this talk because of time.
Thank you for your detailed answer.
Yes.
Hi,
Hi, Dr. Rilett. Thanks for your great presentation. So I have a quick question. So in your HCM6 calibrated approach your research team proposed. So I want to ask about the calibration process. So did you calibrate the VISSIM model, or did you calibrate other parts of your method based on the predicted data? Yeah.
Yes. So is it the question for the reliability or for the reliability one or the passenger car equivalent one?
For the reliability one, yeah.
Okay. So this is a graph, and I went through it. This is a flow chart showing it. So the HCM6 reliability method is based on a Monte Carlo simulation, and it's sort of shown, right here. So each time, for each scenario, they run a simulation, go, okay, today, this 15-minute period, it's, there's bad weather, the volume is this, and then they go through and calculate the travel time, and then they do it again. So it's a Monte Carlo simulation. And so when we were doing, so basically this is their scenario, they get a travel time, they get the metrics, and what we were finding, of course, was they weren't matching. So what we went through, and what we were doing was changing the input parameters to the street value engine. In particular, what we were focusing on was the demand. So they have a demand, you basically put in an average AADT, and they have demand functions in the HCM6 to calculate the travel times. We were playing around, or not playing, we were calibrating those demand functions so that we could replicate the travel time like that. And so what we were doing was adjusting the input parameters to the HCM model so that eventually we would come up with a distribution that matches. I'd be happy to talk offline on it because it's a little bit more complicated than I'm saying, but the reality was we were adjusting their input values in their model so that we could replicate what we were seeing in the field. And then we were trying to come back and estimate, well, what we've made these new demand changes, do they have any physical meaning, or are we just adjusting factors so that we get what we're seeing in the field? And as you can imagine, what happened was the demand profiles in the HCM were very tight, and by expanding them out, saying there's more variation in demand, that was giving us more variation in travel time, which allowed us to replicate the travel times. That's essentially what went on.
Right. Yeah. Thank you.
And I should add, for those of you who are interested, on the slide at the bottom is the DOI for the paper that we discussed here. So there's a lot more detail on the logistics of running the calibration.
Thank you. So is there any other question from the audience? Yes, we are, okay. So yeah, Dr. Komart, he's an associate director of C2M2. He thanked you for your talk.
Thank you. This was it was a pleasure. Like I said, if anyone has any other questions, feel free to reach out to me or our postdocs or grad students. We'd be happy to answer them.
Okay, awesome. So with that, I will ask for the last time if anyone has any other question, or feel free to ask. Oh, okay, so another participant from University of South Carolina, Victoria, she said it's also a wonderful presentation. Everyone understood it, so thank you,
Great.
Dr.
Great. Thank you, Victoria.
So thank you again, Dr. Rilett, for the awesome presentation. And if you, the audience, if you have any question about the webinar information, you can share any question to Charlotte Riggs, Miss Charlotte Riggs. And the recording of today's talk will be found at our Distinguished Speaker webinar series at our CTOMT website, and also it will be available on the YouTube channel. So with all other previous videos are also available in the YouTube channel. So feel free to check all those things, all those information. And with that, I would like to conclude today's meeting webinar. Thank you very much, everyone, especially for your participation. Have a great day.
Great. Thank you. Stay safe.